Have you ever opened a bottle of oil only to be greeted by a stale, unpleasant smell? It's a common experience that can be quite off-putting. That, my friend, is rancidity. Rancidity is the process that makes oil go bad over time. It's like the oil has gone bad, and trust me, you don't want to be cooking with rancid oil. It can ruin the taste of your food and even can make you sick. Rancidity happens when the oil's fat molecules break down. This breakdown is often caused by exposure to air, light, or heat. This breakdown creates all sorts of foul-smelling and often sticky byproducts that taste bad. These chemical reactions involve transformation of fats and oils into their oxidized versions when exposed to air, light, moisture, or bacterial action, producing short-chain aldehydes, ketones, and free fatty acids. These aldehydes, ketones, and free fatty acids are organic compounds. While oxygen is essential for life, it can also wreak havoc on oils. This invisible gas, which we breathe in every moment, has a dual nature. While it sustains us, it can also be a silent destroyer of the oils we use daily. Oxygen molecules from the air can react with the oil's fat molecules. This reaction is not just a simple interaction, it's a complex process that can change the very nature of the oil. It's like a game of molecular tag where oxygen is it. The oxygen molecules chase the fat molecules, trying to catch them and initiate a reaction. These oxygen molecules are like tiny bullies, attacking the fat molecules and stealing electrons. This electron theft destabilizes the fat molecules, making them more reactive. Now let us try two experiments to observe how oxidation of organic molecules leads to rancidity and caramelization. Firstly, I'll cut an apple like this. And now let me keep it in the open for some time. Quite familiar, right? Now look how the apple has turned brown. This is because of oxidation. This visual change is a clear indicator of the oxidative damage happening at molecular level. How does this happen? This unappetizing phenomenon is actually due to a chain of biochemical reactions known as enzymatic browning. When an apple is injured or cut into pieces, the plant tissue is exposed to oxygen. This triggers an enzyme known as polyphenol oxidase or PPO to oxidize polyphenols in the apple's flesh. This results in new chemicals called orthoquinones, which then react with the amino acids to produce brown-colored melanins. Different apple varieties contain different amount of the initial oxidase enzyme and the polyphenols, and thus brown at different rates. Enzymatic browning is not unique to apples. Pears, bananas, and eggplants also turn brown fairly quickly when cut. Enzymatic browning is also responsible for the desirable dark color of prunes, coffee, black tea, and cocoa. To reduce the browning in apples, we keep the slices refrigerated to slow the reaction. You can also coat them with lemon juice or pineapple juice. Fortunately, there's a way to fight against these oxygen bullies. The acids in the lemon or pineapple juices slow down the reaction, and these are antioxidants that inhibit the reaction process. Antioxidants are like the superheroes of the food world. You can imagine antioxidants as molecular shield blocking the oxygen bullies from attacking the fat molecules. These antioxidant molecules sacrifice themselves to keep the oil safe from harm. antioxidants are found in certain foods and may prevent food spoilage. These also include the nutrient antioxidants vitamin A, vitamin C and E, the mineral copper, zinc and selenium. Now let us explore something fascinating: caramelization and oxidation of organic compounds in lemon juice. Here, as you can see, I have a plain piece of paper and some freshly squeezed lemon juice. Let's take a paintbrush and dip it into the juice. Let me write a secret message on the paper. We allow it to dry, and as you can see, the message is now invisible. But here's where the magic happens. I'm going to use the electric iron to heat the paper. Watch closely. As the paper gets warmer, the message begins to appear in a dark brown color. This phenomenon is an example of caramelization. So, what is actually happening here? Lemon juice contains sugars and organic acids. When exposed to heat, the sugar in the juice undergo a process called caramelization, a type of oxidation. During this process, the sugar molecules lose water, which is nothing but dehydration, and undergo structural changes. These changes produce new compounds responsible for the brown color and the sweet, slightly burnt smell. Caramelization is a non-enzymatic reaction, unlike the enzymatic browning we saw in the apple. It's the heat that drives the chemical reaction forward, showing us another form of oxidation in action. Now let us take this concept of caramelization a step further. Let us place some sugar on a heating pan and watch it melt and turn brown. When we heat sugar, it undergoes caramelization. The heat breaks down the sugar molecules, and then the oxidation reaction occurs. The sugar changes its structure, releasing new molecules that create a rich brown color and a complex sweet aroma. Now, let's connect these observations to something which is even more familiar. It's combustion. The wax reacts with oxygen in the air. This reaction produces carbon dioxide and water vapor, releasing heat and light. But what happens when I cover the candle with a glass? The flame dims, and now you can see eventually it goes out. Why? Because the oxygen inside the glass gets used up during combustion. Without oxygen, the oxidation process stops, and the candle cannot sustain its flame. So what have we learned from these experiments? In the browning of apple, oxidation occurs spontaneously due to the presence of oxygen and enzyme in the fruit. In the lemon juice on paper, oxidation and caramelization are heat-driven, not enzymatic, transforming the sugars into new compounds. In the burning of candle, combustion is a rapid oxidation process requiring oxygen to sustain the flame. These are all examples of how oxygen interacts with organic compounds, sometimes slowly, sometimes rapidly, and sometimes spontaneously. Hence, oxidation can be broadly categorized into three categories: slow oxidation, rapid oxidation, and spontaneous oxidation. We also learned how antioxidants play a vital role in slowing down the process of oxidation. Just like lemon juices prevent apple slices from browning, synthetic antioxidants like BHA, butylated hydroxyanisole, and butyl hydroxytoluene are added to oils and foods to prevent rancidity. They act as protective shields, sacrificing themselves to block oxygen from attacking fats and oxygen. So, Let us now see what are the key takeaways. Oxidation is a chemical change where oxygen interacts with organic molecules, transforming their structure. Oxidation is also a process in which the molecules which are getting oxidized lose electrons to oxygen or oxygen-like species. For example, it can be other nonmetals such as chlorine, fluorine, or nitrogen or sulfur. Caramelization is a type of oxidation that happens when sugars are heated. Combustion, on the other hand, is a rapid oxidation process requiring oxygen. Antioxidants are essential in preventing undesirable oxidation like rancidity in oils. So the next time you see a browning apple, a caramelized dessert, and even a burning candle, you will know it's all a part of the fascinating chemistry of oxidation. Thank you.